Welcome back, chemistry students. Today we're going to continue learning about oxidation and reduction reactions, or also known as redox reactions. I'm going to teach you guys how to assign oxidation numbers. In the previous video I kind of gave you guys a little bit of an intro of that, where we put that little number above and we had like the 0 above a single element, and a compound just takes the charge of the element there. But we're going to learn the more like the rules and the more formal way of assigning oxidation numbers. So yeah, let's get this thing started. So an oxidation number is a positive or a negative number assigned to an atom to indicate its degree of oxidation or reduction. So that's that little number above. Let's see here, I'm going to skip ahead to that. Let's get to the first rule here. So the oxidation number of any element in the free or uncombined state is 0. And I introduced this on the last one here. So if you have a pure element that isn't combined with any other element, the oxidation number is going to be 0. So if you have pure bromine, even though it might say Br2, because that's the formula for it, it's still uncombined. It's not with any other element. The oxidation number would be 0. So carbon would be 0 if you had pure carbon, pure sulfur, pure potassium. So that's one of the very first rules. So let's go through this list of them. Rule number 1 says the oxidation number of a monatomic ion is equal in magnitude and sign to its ionic charge. So if we have sodium chloride, NaCl, this would be like a monatomic ion, is going to be equal to its charge. So sodium chloride is a neutral compound. The oxidation number for the sodium would be +1. The oxidation number for the chlorine would be a -1. So that's going to be the charge. Okay. Rule number 2. So that's in a compound. So you just take the charge. The oxidation number is the charge. As simple as that. We kind of really word it all in here. But if you got a compound, it's just equal to the charge. Rule number 2. The oxidation number of hydrogen in a compound is going to be equal to +1. There is an exception to the rule. If you have a metal hydride, then it's going to be a -1. So if you have sodium hydride right here, this would be a -1. But any other time, the hydrogen is just going to be a +1. Rule number 3. The oxidation number of oxygen in a compound is going to be -2, except in peroxides. So like when we have here H2O2, this is hydrogen peroxide. So this is an example where the oxygen is going to be a -1 for an oxidation number. But in general, oxygen is going to be a -2. All right, number 4. That's the pure element rule is equal to 0. Number 5 says for any neutral compound, the sum of the oxidation numbers of the atoms in the compound must equal to 0. That's very similar to this rule as well. So it's going to add up to 0. So if you got a +1 here, you got a -1 here, the oxidation numbers in this compound must add to 0, which it does. Then rule number 6. This is going to be for a polyatomic ion. Okay. The sum of the oxidation numbers must equal the ionic charge of the ion. So for instance, if we have NO3, which is nitrate, let's call this, it has a -1 charge here. So let's apply this rule. So oxygen is going to have a -2 charge, okay? I'm going to put this in parentheses, it'll be easier to see. So if you have a -2 for an oxidation number here, you have 3 of them, so then overall you have a -6 from the oxygen. So the nitrogen must be a number, okay, that when it's added to -6, it equals -1. So in this case, the nitrogen must be a +5. Because when you add this to the -6, you're going to get the -1, which you need. So that's how we can assign the oxidation number for like the nitrogen and the polyatomic ion. I'm going to show you guys a bunch of examples. All these rules are going to make sense. It's really not that difficult. So here's another example. So you have H2O. So oxygen's a -2. So then therefore the hydrogen must be a +1. Alright, so let's look at this one here. Let's assign the oxidation numbers of potassium chromate and the chromate compound. Alright, so let's start with the outsides. So oxygen is going to be a -2, we know that. Potassium's a +1, that's from the periodic table. Alright, and it's a neutral compound. So the chromate must be a number that when added together, you know, when we add all those oxidation numbers up, it should be equal to 0. Alright, so from the potassium, I'm just going to write this down here, we're getting a charge of +2. From the oxygens, we're getting a -8. And when you guys are doing this, you're going to do this in your head. So then what must the charge be, or the oxidation number be for the chromate? You should see that it should be a +6. Because when you add that up, it should be equal to 0. So you have +2 plus 6 gives you a +8. And then the minus the 8 will give you 0. So this stuff you'll do in your head. I just wrote it down so you can see it. So this number is a -2. This number is a +1. That's basically the rules, right? The one that can change is the chromate. So there it is, the chromium. Let's look at the other one. So this is going to be a -2 because that's the oxygen, okay? So I suppose I'll show this step in the head here. This gives us a -6. So then what must be the oxidation number of the chromium be? Well, it has to be something that when added to -6, it gives us 0. So this must be like a +3. Okay. And here's what's kind of fun about this slide is we have this chromium. So the color is from the different transition states of the chromium. So when chromium has an oxidation number of +6, it's yellow. When the chromium has an oxidation number of 3, then it is going to be green. Okay, let's practice a bunch of these. So we have what is the oxidation number of each kind of atom in the following ions and compounds? So I'm just going to write it down here so I have more room to work. One of the rules is oxygen is always going to have an oxidation number of a -2. So then what must be the sulfur? That should be pretty easy to see that it is a 4 because +4 because it has to add together to give you the 0 there. Okay, letter B, we have CO3. But here's the deal though. The final charge, because this is a polyatomic ion, the final charge must add up to give you a -2. So if we say the oxygen here is a -2, but you got 3 oxygens, so then overall it's -6. So what must the carbon be? The carbon's got to be a 4. And I can write that down here. So this is what I did in my head. I said, okay, overall I got a -6 with the oxygens. So then what must the carbon be, right? The carbon must be a +4 because when you add these together, you get a -2, which is the charge on the ion. Okay, so the carbon, so let me rewrite this down here. So the carbon has an oxidation state of +4. The oxygen is a -2. The compound itself has a charge of -2. So that's how you figure those ones out. Alright, so let's look at letter C. Here's one where I like to attack the ends and then fill in the middle. Sodium is a +1 for sure. Oxygen's a -2 for sure. So the sulfur is what we have to figure out. So I'll do the steps that I do in my head here. So from the sodium we have a +2. From the oxygen we have a -8. It's a neutral compound, right? There's no +2s or -3s at the end. This is a neutral compound. So then therefore, what must the sulfur be? Well, the sulfur must be a +6. So I can put that right in here. because then when you add all that together, it gives you 0. All right, let's look at letter D. This one, don't be scared of it just because you got the parentheses there. It's not too bad. So you got ammonium, which is NH4, and you should know that this is a polyatomic ion. Ammonia has a +1 charge. You should have that memorized, okay? The sulfur, that's a given. That's going to be -2. So what we have to figure out is what is going to be the nitrogen, what's going to be the hydrogen. Hydrogen is going to be a +1, okay? So now you have a +4 here. So the nitrogen must be something that adds to +4 that gives you a +1. So that should be a -3. So I'll put that here. So it's a +1. This is a -3. And then there it is. All right, let's look at a couple more here. It says determine the oxidation number of each element in the following here. Maybe we'll just do ones that might be a little more trickier. Let's do this one and this one. All right, so, well, oxygen, that's -2. So the phosphorus must be a +5, and that's because I did this in my head. I said, okay, well, this is a -10. It's got to be a neutral compound. So this one's got to be like 2 times that, which would be 10, or which would be the 5. All right, so now let's look at the nitrate. This whole thing has to add up to that -1. So if you got a -2 here, that'd be -6. This must be a +5. Let's see here. I think I will leave those ones up to you guys. So let's get to this. So why are we assigning oxidation numbers? Well, if you remember right in the last video, the oxidation numbers helps us to determine what's being oxidized and what's being reduced. So like it says here, an increase in the oxidation number of an atom or ion indicates oxidation. So when that number increases, it's going to indicate oxidation. So if we have element A and then element A on the other side, and let's say element A goes from 0 to a +3 with that oxidation number, that is suggesting that it lost electrons. So if you remember, right, oil rig, if we are losing electrons, we're getting oxidized. So any element that's going from like a 0 to a +3, any sort of increase in the oxidation number, that element's being oxidized. All right. And then on the flip side of things, a decrease in the oxidation number is going to indicate reduction. So for instance, if we have an element A with a +3 charge, and then element A goes down to a 0 for an oxidation number there, you can see that it's going from a +3 to a 0. That is suggesting that it gained electrons, because that's a way to reduce that oxidation number. And if it gains the electrons, it means that it's being reduced. All right, so here's an example. We have copper that's being reacted with the silver nitrate. This is a single replacement reaction. You can see the two are going to be switching spots. The oxidation numbers have been assigned for us already. So if we're trying to figure out what's being oxidized and what's being reduced here, we can do that just by looking at the oxidation numbers. Like I said, I like to look at the metals because that's where the action is happening here. So the copper is going from a 0 to a +2. Well, we have an increase in that oxidation number. That must mean, well, 0 to a +2, that must mean it lost some of its negatives. So, boom, it lost its negatives. This one's going to be, and if it's losing, that means it's going to be oxidized. If you look at the silver, it's going from a +1 down to a 0. Well, that must mean that one is being reduced because it's gaining those electrons. All right, let's skip over that. So let's look at this example here. Use changes in oxidation number to identify which atoms are oxidized and which atoms are reduced in the following reaction. Also identify the oxidation agent and the reducing agent. So once you guys get good at assigning oxidation numbers, this is a piece of cake. So Cl2, hey, we have a single element, right, by itself. So that's a 0. HBr, well, that just takes the charge for the oxidation numbers. HCl, same thing, just takes the charge. Bromine, there you go, that's a 0. So then when you're looking at it, look at what's happening here. Okay, well, the chlorine is going from a 0 to a -1. So 0 to a -1, that's suggesting that it is gaining electrons, so that means it's being reduced. I'm just going to abbreviate that as reduced. Let's see what else is happening. Well, the hydrogen is going from a +1 to a +1. That didn't change. There's nothing's happening to that. Let's look at the bromine. The bromine is going from a -1 to a 0. So that number is going up. It's becoming less negative. So that must mean that it did what? Hopefully you guys can see that it is oxidized because it lost those electrons. Okay, so now we've picked out what's being reduced, what's being oxidized. It's pretty simple to do the other part, because if you remember right, you just flip the terminology here. So that's going to be the oxidizing agent, that's going to be the reducing agent. Alright, let's try one more here, and then I think we'll call it. So let's look at letter B. So I'll rewrite this one. NO3 goes to this. Alright, let's start by assigning the oxidation numbers. For me, I like to find the zeros. So there you go, there's a 0. Let's kind of keep looking around now. Let's go to the first one. Potassium, we know that's going to be a +1. That's just a given. This oxygen is going to be a -2. We have a polyatomic ion there. You can kind of do the sandwich method for this one as well. So you know potassium's +1. You know you got a -6 from the oxygen. So that must mean that nitrogen's a +5. And on the other side of things, this will be a +1. This will be a -2. So you can figure out what the middle is going to be, that nitrogen. And this time, it's going to be a -4 and then a +1. So that must mean this nitrogen is a +3. Okay. So this one's kind of different because we got a non-metal that's happening here. All right. So the potassium is going from a +1 to a +1. Nothing's happening. The nitrogen, however, okay, something's happening with that nitrogen. It's going from a +5 down to a +3. So that's suggesting that its number got reduced, which means it gained electrons. So the nitrogen is the substance that's being reduced. Let's look at oxygen. Well, the oxygen is going from a -2 to a -2, but there's a free and uncombined oxygen that's a 0. So that means that that guy just got oxidized. The number went up. So this would be, then if you flip the terminology, the oxidizing agent, this would be the reducing agent. All right. And I think I'll leave that for you guys. You guys do have a Schoology assignment, 20.2.